4-frequency symmetrical probing. Two pairs of probing signals shifted from the carrier are sent to the mediums of the left and right slopes of BNF. Bragg wavelength of BNF is equal to the carrier wavelength, different frequency inside pair is equal to 100 MHz. The outputs of photodetector signals are formed, corresponding to the beating of the first, channel 1, and second, channel 2, signal pairs. By measuring the difference between amplitudes of each beating envelope, one can unambiguously determine detuning sign and value of central BNF wavelength. 3 cases of DNF deviation are shown in 3 cases of BNF deviation for 4-frequency method. In the first point, the BNF offset from the resonance wavelength is absent, and the output amplitudes of beating envelopes are equal. In the second point, there is a slight BNF deviation, and the direction and magnitude of the deviation are determined by greater amplitude of beating envelopes. In the third point, there is a significant deviation, and the direction and magnitude of the deviation are determined by the presence of a signal of beating envelopes and its level in one of the channels. OSNR problem for CD monitoring in synchronization channel. For experimental part, we chose 3-frequency method, as less compliant in comparison with 4-frequency one. The procedure for monitoring the position of the BNF in synchronization channel can be implemented to RFCS method realization structure. In this case, it contains one narrowband photodetector with a 10 GHz band and filters tuned to frequencies at 0, 100 and 200 MHz from the carrier with a bandwidth of 10 MHz. The procedure for such analysis relates to inline monitoring procedures, and the arrangement of frequency components at a frequency of 100 MHz from the frequency of the RFCS allows us to speak about identical for all 3 constituent CD parameters and the corresponding identical change in their amplitudes as it increases or decreases. Using the algorithm for approximating BNF spectrum by the Gaussian curve at each measurement makes it possible to increase the accuracy of determining its central wavelength by an order. Without going into the details of the physical nature of the phenomena, the level of the main noise of the photodetectors is higher than the level of background noise of scattering in the fiber and elements of the installation and determines the possibility of detecting the received signal. The gain in improving the OSNR in comparison with single frequency measurements on the RFCS is determined by the following expression. Illustration for OSNR gain catch for 3-frequency probing method, noise, spectral characteristics of noise for photodetector realizations bandwidth BWPD. 3-frequency probing method has complex gain parameters and characterizes only by one disadvantage of large current noise filtering on DC component. Where S equals SFTF is the spectral noise density of the receiver, BWPD is the bandwidth of the PD equal to 10 GHz, and VW3 is the frequency band of filters, 10 MHz, at frequencies of 0, 100 to 200 MHz. The gain is determined by the different filter bandwidth, nature, and noise level in different frequency regions SF for different types of photodetector, with bandwidths 10 GHz, and filters, with bandwidths 10 MHz, respectively. In filter regions near 100 and 200 MHz, there are only thermal and shot noises. Current noises are characterized only for narrow DC filter. Taking into account the given data, the gain in OSNR can be 10 to 12 decibels. Thus, when using inline CD monitoring with a preliminary amplitude modulation of the RFCS, the gain relative to the OSNR compared to the monitoring at one frequency of the RFCS can be 10 to 13 decibels. Thus, CD analysis on the RFCS can be carried out, starting with a classical OSNR in 3 to 5 decibels.